Thermochemical equations. With thermochemical equations, we kind of re-look at stoichiometry as we do these conversions with energy now. But to do them, we have to integrate a new relationship. It's the enthalpy-mole relationship, enthalpy equal mole relationship, which we get from the balanced equation. Now note, if you're going from mole to kilojoules, in a stoichiometry problem converting from moles to kilojoules, you would multiply by the enthalpy-mole relationship, the new relationship. If you are going from kilojoules to moles, you use the same relationship, but the fraction of course flips, so that kilojoules are on bottom and moles are on top. If you're going from moles to kilojoules, the moles are on bottom and the kilojoules are on top. The other type of problem we see with the thermochemical equations, particularly on the worksheet that we got, is when we're converting from grams to kilojoules or kilojoules to grams. Now, because this is not straight from mole to kilojoule, that means that there's not just one relationship, but rather two. Grams must first be converted into moles before they can be converted into kilojoules. Same thing if you're going the opposite direction. Kilojoules have to be converted to moles before they're converted to grams. So, to get from grams to moles, you have to multiply by the molar mass, which is an old relationship. Reminder, that's the same thing as the atomic mass if it's a single element. If it's not a single element, you look at all of the formulas, all of the letters, etc. And if there's two O's, that means you're going to take the mass of O twice. Let's assume that that's 16. So 2 masses of O plus the mass of your next element, in this case hydrogen, so the mass of 1. So that's how you would find the overall mass, which would be, in this case, 33 grams equal to 1 mole. That's just an example of how to find molar mass. The next relationship will take you from moles to kilojoules. That's the new relationship, that enthalpy-mole relationship. That's a number of delta H equal to some number of moles from the balanced equation. Now, both of these can be found in the balanced equation, or thermochemical equation. Sometimes delta H is found at the end separate. If it's in the balanced equation, it won't say delta H. Instead, it'll just have kilojoules on it. So the number of kilojoules equal to number of molar mass is also a true statement. Okay? Now, still, you're going to be finding your known and unknown because this is still basically stoichiometry. But it's either going to be this one fraction that you're going to be multiplying by, your known times this one fraction, or you're going to have this your known times 2 fractions. You must find your known and unknown to know which. Alrighty guys, so now let's go ahead and put into practice one of these thermochemical equations. We have 2 examples. We're going to do the first one, and I'm going to zoom in a little bit so that we can see a little bit better. Okay. Like I said, this is still basically a stoichiometry, so we need a known, an unknown, and we basically know that it's either going to be one relationship or 2 relationships. Let's solve. Reading through the question, the combustion of ethene, C2H4, is an exothermic reaction. Use the information below to determine the amount of energy given off when 2.3 moles of ethene is combusted. This is the balanced equation. Note that delta H is not in the balanced equation. Instead, it's at the bottom or underneath, or at the end if you're considering it that. So I see that there are 2.3 moles of ethene, the formula of which is C2H4. My unknown is, I'm looking for to determine the amount of energy. So I'm looking for question mark kilojoules. So since my known is moles and my unknown is kilojoules, I just need to use one relationship, and that relationship is the enthalpy-mole relationship. To get the enthalpy-mole relationship, I'm not actually going to write it, but I'm going to go over here. I'm going to find ethane in the balanced equation and circle it. This says 1 mole. I'm also going to circle the kilojoules in the equation. Note that it's at the end after a delta H, so I don't have to figure out the sign. 1 mole of C2H4 for every negative 1,390 kilojoules. That's going to be my relationship. Let's set up our stoichiometry problem. Put your known down first, always. You can turn this into a fraction if you want. I'm going to. I like to. Then, since we had one relationship, we have one fraction. We need to plug that fraction in. This relationship was the enthalpy mole relationship. Because that's moles, we want moles on bottom. Because it's the same unit as up here. And we're going to put kilojoules on top. There's 1 mole here. There's negative 1,390 kilojoules here. Moles of C2H4 cancel. Go ahead and calculate it. 2.3 times negative 1,390. Divide by the numbers on bottom. Divide by 1. Divide by 1. Your answer should be, for this problem, negative 300 or 3,197 kilojoules. Alright guys, we'll do the next problem in a second. Alright guys, continuing with thermochemical equations. We previously have done a mole to kilojoule calculation. We're now going to look at a second calculation. The second example says how much heat in kilojoules is needed to produce 1,850 grams of ammonia, NH3, according to the following reaction. Note this balanced equation and the delta H at the end. It's not in the equation this time. It's not in the equation this time. It's at the end or underneath in this case. So remember, we need to find our knowns and unknowns before we can even determine how many relationships there are. The known in this question is 1,850 grams of ammonia, which is NH3. And our unknown is how much heat, and specifically in kilojoules. That's the unit we're looking at. So now we know we're going from grams to kilojoules, and when we look back at the relationships for planning on this, grams to kilojoules involves 1-2 relationship. So this is going to be a 2 relationship problem. Because we're going from grams to kilojoules, the first relationship is going to be molar mass. The second relationship from moles to kilojoules will be the new relationship, the enthalpy mole relationship, which I'm just going to write as new because it is pretty new for us. Okay, so first things first, we need to find the first relationship. The one that's going to go first is the molar mass. Find your molar mass by taking your elements, nitrogen, hydrogen, and finding their atomic masses. Nitrogen's is 14.007. Hydrogen is 1.008, but there's 3 of them, so you'll need to multiply it by 3. Plug that into the calculator, and that's going to be how many grams you have per 1 mole of ammonia. There we go. So the molar mass is 17.031 grams per mole. The new relationship, as a reminder, is found in the balanced equation. You circle the necessary or the known or unknown element or compound and the kilojoules. So we're going to go and do that now. Going through here, we find NH3, it's 4 moles of that. And we're going to circle the kilojoules right here. So we got 4 moles for every 1,530 kilojoules. This does have a delta H in front of it, so we know that this is supposed to be positive. We don't have to figure that part out. Okay, now we just plug it into our or make a calculation. You're going to put your known down first. You can make it into a fraction. I think I'm going to do that. Remember, this is the known, not the relationship. There's 2 relationships, so you need 2 fraction lines. The first relationship was molar mass. It is 17.031 grams per 1 mole. This first fraction, we need to decide what goes on bottom. Since grams is on top here, grams should go on bottom here. And that means the mole part's going to go on top. Well, up here, 1 mole, so 1. 17.031 grams. Okay, plug that in next to the grams. With this set up correctly, actually I should put NH3 on it. There we go. With this set up correctly, now we can go to our second relationship. Remember, this is 4 moles of NH3 for every 1,530 kilojoules. Looking at this unit and deciding what we want to put on bottom, these two units need to be the same, so the moles of NH3 need to go on bottom. That's a 4. We put the other half of this relationship on top. That's the other thing we circled, 1,530 kilojoules. The next thing you're going to want to do now that everything's plugged in is make sure all of your units cancel. You got same unit here and here, they cancel. Same unit here and here, they cancel. The only unit that doesn't cancel, kilojoules. Next we multiply. I multiply all my numbers on top of my fractions and then I divide by all my numbers on bottom. Remember, there's more than one way to solve for these problems and calculations. 1,850 times 1 times 1,530 divide by 1, divide by 17.031, and divide by 4. We get a really big number. We don't need everything in this. We actually technically only need 1, 2, 3, 4, 5 significant figures. No, wait, 1, 2, 3, 4 significant figures, but I'm going to go ahead and write it up to the ones. Here we go, 41549 kilojoules. That's our answer. Go ahead and make sure you turn that in. Or actually, sorry, this was a question from your worksheet, but this has been the second type of thermochemical equation. If you are having trouble with that, make sure you watch the first video, then rewatch the second video, or come in and ask me for questions, or ask me questions if you have any questions. Thank you, and have a great day.